So we're trying to finish naive Bayes today. Just a couple of notes. You all probably saw the overview deadline has been pushed back. I strongly encourage you not to wait till the end of that deadline. The Google poll went out as expected. There is no one intersection with all your. So I'm going to be sending individual emails to a few of you. The crucial ones, so if I can manage to nudge, will cause a non-empty intersection. So you'll hear from. Okay, and you know your return. Alright, so let's get started with naive Bayes. So what we're doing today is, I'd like to, so last time we presented why naive Bayes is a good idea, but I'd like to present another view of naive Bayes today. And I'd like to start with this entity that we met a couple of lectures ago called Bayes error. We had we had written down something called expected loss, and we said, it breaks down into a few different dimensions. You may be making mistakes due to different reasons. One of the mistakes that you just can't get over is the best thing that any machine learning method can do on this particular problem. Right? And we'll call that Bayes error or Bayes loss. And we'd like to know, so this is the best that any machine learning algorithm can do, but is there one that does achieve it? And what does it take to get the best performance? How would you get best performance? So you get best performance if if all of these other three are zero. You're solving NP-hard optimization problems, if you have infinite data, and your model is essentially complete. It contains reality and it is a special case. Right? If all of those are zeros, what do we get? How do we achieve this thing? Okay? And we'll call those Bayes classifiers in terms of classification problems and Bayes regressors for regression problems. And it will actually tell us that if you want to achieve Bayes error, you should write down a particular kind of Bayes classifier. We won't be able to do that, so we'll write down a naive Bayes classifier. Okay, that's the path that we take to naive Bayes. Does that make sense? Okay. So let's do that. So we're introducing the concept of Bayes error, the best that you can expect to do. Right? If you recall, we wrote down something called expected loss. We wrote down that x and y are some random variables, and they're coming from some distribution x over y. I'm using p star, even though last time I used p, just to emphasize the fact that this is an unknown distribution. They're coming from something that we that's reality. We don't know what that is. Okay. And we wrote down expected loss as integral over the space of x, whatever that may be. If this is a continuous space, this is something like RD. These are multiple integrals. This is the space of y. We write down some loss function of y comma y hat, probability of x over y. Okay. And this is reality. This is what you predict after looking at x, and you pay some loss. That's the probability with which you're getting data sample from, and you integrate those two out. And this is the expected loss, right? Let's try to think about what is the lowest that this can possibly be. Like the smallest possible value of this over all possible predictors. What is the best thing that we can actually output that will minimize this expected loss function? How low can we take this? Okay, and let's make certain simplifying assumptions. Let's say we're dealing with the classification case. So, this space is not a continuous space. It's not an integration, because this space is just 1, 2, 3, 4 all the way to k. Right? This is just multi-class classification. The other assumption that we'll make is we'll use a natural loss function for classification, which will be the 0, 1 loss. Okay? So loss of y comma y hat is 1 if y not 2. Okay. So far, just fairly straightforward settings. So if, first of all, this is classification, then this is not an integration, then this just means I need to sum this for y equals 1 to k, right? Okay. And what the other thing that I'll do here is I'll just rewrite this as, and d of y goes away obviously, it's not a continuous variable. I'll rewrite p star of x comma y as p star of y given x times 2x. So far, that's just chain rule, right? I haven't done anything. There's a star here as well. Okay? Let's just chain rule applied in the joint problem. And I'll try to appeal to what you have seen before. What does this look like? Looks like the, can we group these terms together?
Expectation of
correct. It looks like the expectation of whatever this ugly thing is, right? There's some density function, there's an integration, there's an expectation of something. So let's make that simpler. So this is just expected value over p star of x of summation y equals 1 through k y equals y hat p star of. Okay. So this is expected value over how x's are sampled. This is input, so we don't care about that. It's this quantity that we care a lot about. So for actually what we'd like is over all possible inputs, you'd like to keep this small, right? And here's something that, so this is, given this x, how likely is this y under reality? Reality may be deterministic, in which case these probabilities are zeros or 1. Or reality may be probabilistic or stochastic. Reality may have noise in itself. Does that make sense? If reality is deterministic, then there's a 1-to-1 mapping between x and y, or many-to-1 mapping, such that the answer is, the probabilities are 0 or 1. And here's the loss that you're paying by predicting y hat when the right answer is y. Does that make sense? For 0-1 loss, what does this look like? I'm just going to expand out the summation. It looks like this, right? It was loss times probability, so loss of 1 comma y hat times p star of 1 given x plus loss of 3 comma y hat times p star of. Right? I've just expanded that summation now. Let's say, what is the probability that class 1 is the right answer here, and what is the loss that you pay if class 1 was the right answer and you predicted y, and so on. Okay. So it should be pretty clear that these losses we've assumed are 0, 1. There's only one of these loss functions that is set to 1. There's only one of them that is set to 0. Else is y hat. So if you predict the correct thing, your loss is 0. Everywhere else, your loss is 1. So there's a summation here. Most of these terms are actually 1. There's one of them which is 0. So there's one term which is missing. So I can write this whole thing as. So that one term that's missing, I can add that one term and I can subtract that one term. If I add that one term, the summation becomes 1 minus p star of y. Does that make sense? If I add that one term that is missing, because everything else is 1, it's just a bunch of probabilities being summed up. And so that just becomes 1 minus that I subtracted one term that was missing. Okay, so very nice. So this is exactly what I needed. So we want a predictor that minimizes this expected loss function. It's the same thing as a predictor that maximizes this, right? For every value of x, if you can maximize this, then you have minimized this. Because minimization of something sitting inside an expectation, if you can minimize it over all possible values of x, then you have minimized the expectation as well. Does that make sense? We wanted to minimize this over, here's expected loss. If you can maximize this, then this quantity is minimum for every value of x, and therefore must be minimum no matter what probability distribution you use. Right, so this is equal to max over y hat of p star y equals y hat. Very nice. So this is something, this is Bayes error, right? This is, yeah, right here. This is Bayes' error. This is the best we can possibly do, and it turns out that if you want to achieve that Bayes error, then all you have to do is somehow know for every input what is the probability of the output and just pick the highest one. That's it. This is just with most confident class. Right? If you have a classification problem, there's probably just some histogram with 1, 2, blah 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 to the k. There's some weights, just pick the highest one. And something as simple as that gets you the best possible thing that you can do. Does that make sense? Is that right? So probability of y given x is just a discrete probability. It's just a discrete distribution. It's a histogram that sums to 1. So just go to that histogram, pick the highest bar. That's this maximum a posteriori predictor, right? I can also call this as y hat MAP. It's the posterior distribution of y given x. What do you believe about y if I tell you x? If you just pick the highest one of that y hat maximum posterior is also the one that achieves the lowest possible error that you can possibly get. That makes sense? Mm-hmm. Okay, so this doesn't seem so hard. Discrete distribution, just have to find, write a for loop, find the highest one. Why can't we do this? No, it's discrete.
We don't have y.
What?
Why you don't have y?
You don't have y?
The reality.
You don't have the p star.
P star.
Exactly. So that's actually one of the reasons why I emphasize the star. Like, this is not coming from your model. This is coming from reality. Everything you wrote down was under whatever the true distribution was, which we don't know. We just see the samples from that. So if somehow we knew what the true posterior distribution was, finding the, doing this easy stuff would be the best thing to do. But here's the hard part, right? I just hate the hard part into this notation, right? I said if you knew that, then everything's easy. But that's the hard part. That's what all of learning comes in, right? We have to find this distribution, we have to fit this to data, and then make the prediction. Does that make sense? So this is Bayes error, and this is a Bayes classifier. A Bayes classifier is one that actually achieves Bayes error. Right? Bayes error is the smallest possible error that you have to make. You have to pay this loss. You cannot do better than that. The reason why you cannot do better than that is because there is just some non-determinism in your system. Right? That the true distribution of y given x is not a 0-1 distribution. Does that make sense? And a Bayes classifier achieves Bayes error, and apparently the best way to reach a Bayes classifier is just find the posterior probability. Okay? And that's where there are two approaches of doing this. There are two ways of finding this posterior distribution. And this is what we talked about. The generative approach is one that actually estimates not P of y given x from data, but actually estimates P of x given y from data and P of y from data, and uses Bayes' rule to come up with P of y given x. And then make this prediction. This prediction is the easy part. It's the estimation of this that's the hard part. Does that make sense? It's just P of x given y. What does this feature look like given this class instead of class given feature? Does that make sense? So this is a generative classifier, and a discriminative goes for this directly. So you try to model the posterior directly. You do not try to estimate P of y, you do not try to estimate P of x, you just go for P of y the next directly. Okay? Okay, so we're talking about generative classifiers, we're talking about Bayes classifiers. Bayes classifiers are Bayes optimal or achieve Bayes error, and this is all under the assumption that this is a 0-1 loss function. If we had written some other loss function, then this derivation would be different, and therefore this would not be the right thing to do. Does that make sense? Different loss functions lead to different kinds of predictors. Okay, so we're taking the generative approach. We have to estimate the probability of x given y, probability of y. And that's what we did last time when we did a counting argument. We said that the first one is difficult to estimate. The probability of all the features is really difficult to estimate the joint probability because there are just too many features. We said that if there is a there's just too many numbers here to estimate. If there are, if each feature takes 2 states, then there's 2 to the d minus 1 entries in this table. This is a distribution over d things, right? Each can take 2 states, so there's 2 to the d possible states. It's a distribution, so I have to subtract 1, and there's times k, 1 for every setting of class, right? This is far too many parameters. It's far too many parameters, and therefore when you try to estimate it from a small data set, you're going to run into overfitting. Because you're never going to see, a particular configuration of these variables. X1 is set to true, X3 is set to false, X5 is set to true. That tuple will just never happen. So when you go to your training data, you do a search for that tuple, answer will be 0. I've just never seen this particular configuration before. Does that make sense? Okay. And so this is, if you could estimate this, and you did use Bayes' rule to come up with y given x, and you did this, that would be a Bayes classifier. That would be a true Bayes classifier. And that's why we came up with a hack that we called it the naive Bayes classifier. The naive Bayes classifier is a Bayes classifier, but it makes an extra assumption that this distribution of features given y is actually just equal to the product of that I can just consider each feature on its own. I can just measure the dependence, what does this feature look like for this class on its own, and I can multiply those two together. Right? That I don't have to estimate all these particular configurations jointly, because I'm assuming that the features are, if you remember our notation, xi is independent of xj given y. They're conditionally independent. Okay? We're not assuming that the quantities that you go out and measure into the world are completely independent or uncorrelated. We're just saying, if I tell you what class they came from, then they're independent. Then you don't gain any additional information. That makes sense? Okay. So this makes life simpler, because here we have to estimate numbers in a really large table. Here, each one of these things is just a table. Right? It's y can take some particular values from 1 all the way through k, and xj can take some values all the way to 1 or to whatever cardinality of xj is. I'm generalizing this to discrete features as opposed to just binary features. Right? You have to estimate this table, and you have to estimate the prior probability of y, which is just a vector. Okay, so if I give you a data set and I ask you, how do we estimate this? We've done this before. How do we do that?
Don't you count how many times that is true divided by the...
Exactly. So if these are the parameters of your distribution, this is a categorical distribution. You've done this in your homework. This is a categorical distribution. All you have to do, if I call this by shorthand of pi y or pi c, then all you have to do is just count. Count how many times you see y equals y divided by n in your data set. Right. Just go ahead, run a for loop, see how many instances you have of a particular class. And this is maximum likelihood estimation. Right? So it's theta at MLE of that. Right? This is a categorical distribution, and I argue that such a table is also a collection of categorical distributions. If you think about it, every column here, right, every particular column in this matrix is a categorical distribution. Does that make sense? If I tell you what y is, then this is a categorical distribution over x, right? It just sums to 1 over all the settings of x. So how would you estimate the numbers in this column?
Same thing.
Same thing. So what you do is, let me say this, if we're talking about the jth feature, and let's say this is the cth class, this is a number theta jc of a particular value, let's say a. And that's the probability of xi given a, xi equals a given y equals c. That's our shorthand for what is the probability that this feature takes this state while the class, given the class takes that state. And this is what you're estimating in your homework. This is what you have to implement. We're just showing this for a discrete setting or a categorical setting. You have binary features. And the way to do this in a maximum likelihood estimation manner is exactly the same. Go ahead and, in your data set, count how many times you've seen xi set to a while y is equal to c divided by count of y equals c. Thank you. So really, this is a for loop. If you think of your data as a matrix, on the rows are each data point, the columns are each of the features. You just have to keep track of two columns, the ith column and the class, and you just keep going down over the entire thing. Check whether you have ever seen a data point with the ith feature set to this and the class being c, right? And count how many values you have of that particular class. And this is the MLE estimation of this parameter. Does that make sense? So this was all intuitive and sort of hand-wavy, but you can actually show that this you've done in your homework. You've shown that we know how to do pi hat MLE. This is also pretty easy to show that these are just a collection of categorical distributions. It's not hard, you reach the same result. And if you think about it, this is the same thing as just saying your world is conditioned on y equals c. Right? The only data points you're interested in are the ones where y is equal to c. And so this becomes n, the number of data points, and this is the quantity that you're counting. Does that make sense? So in your homework problem, the senator stuff, this is a Republican or a Democrat. These are the votes for a particular, whether or not they voted for a particular bill or not. You're just counting how many Republicans are there, how many Democrats are there. For all the Republicans, how do they vote? For all the Democrats, how do they vote? Does that make sense? On a particular bill. Okay. So imagine now if you had not made the naive Bayes assumption. Imagine if you had to estimate this entire table. What you would have had to do is this count would be much more difficult, right? This count would have said xi equals j, x1 equals little x1, x2 equals little x2, all the way till this entire tuple. And the answer every time would have been 0. Right? Because you've never seen, for most of the tuples, the answer would be 0. You haven't seen most of the tuples. Right? And so most of your estimated probabilities would end up being 0. Most of this would be 0, and therefore the probability of y would be not defined in a lot of the cases. Does that make sense? Okay. So given that we've done this, the prediction for naive Bayes is pretty simple as well. So instead of P star, that's your P star, this is your estimated probability, and x equals little x, and this is just equal to probability of j equals 1 through b, xi equals xj equals little xj, and then y equals little y, little y, divided by probability of x equals little x. Right? I've just written the Bayes rule with the assumption of naive Bayes chained in. This is the posterior distribution of y given x. This is x given y, Bayes rule, and the naive Bayes assumption. And there's an argmax here over y. And so all we care about are these numerators. And so this, you can sort of ignore this if you're only concerned with the argmax. It's just a normalization constant. Right? So all that you're asking is, how likely is this class? Just a priori, how likely is this class? How much does it explain feature that I've observed? Right? This patient came in with this symptom. How much is that explained by this particular label? Multiply all of those together and just take an argmax. Right? This is just a list of k categories. And sometimes, if you take the log of this, argmax of log is the same thing. A lot of times you'll find in literature this written like this. Argmax over y of log u of y plus summation j equals 1 to t of probability of x to If you just take the log of this entire thing, it just becomes summations. And this is going to be interesting later on because we're going to try to link up this as some linear combination of some features, and we're going to make this a bias term later on. You don't have to worry about that right now. Does that make sense? As far as we're concerned, these are just completely equivalent. Okay? Okay, so we know what a Bayes classifier is. It's something that achieves Bayes risk, and we can prove that Bayes risk is the minimum possible thing. And so we know that our decision rule consists of this. This is the Bayes rule in log space. This is what we want to predict. We have a generative approach and a discriminative approach. We talked about that. And last time we talked about generative approach has an advantage that you can actually generate a sample. Somebody came up to me at the end of the class and asked, why do we care about generating a sample? If we have probability of y and probability of x given y, yes, that allows us to generate a sample, but why do we care? In certain domains, it's often possible to generate samples and go to a domain expert and show the generated samples, and they can tell you whether or not this seems realistic or physically plausible or biologically plausible, right? You cannot do that in these kinds of models because all you've learned is probability of y given x. You cannot generate a new sample. You can just make predictions on new data that comes in. And some of the models that we're going to look at don't even formulate this as a probabilistic task. They're just directly going to learn a function that given an x gives you +1 or -1. So they don't even talk about probabilities. So things are not going to be calibrated in those cases. But we're getting to that. Okay, let's see. The parameter argument. So this is the naive Bayes assumption that your features are factorizing. Let's see. Here's how we're predicting. Okay. So let's do this. Let's do a demo in class where we try to demonstrate what naive Bayes would do. Here's the demo that I'm going to try to work through. Here are my variables. So I'm going to try to predict whether or not you did not watch. Super Bowl was a month ago, right? There was an event called Super Bowl. I missed it. Something that happens. I walked into the grocery store. The guy asked, "Are you following the game?" And my response was, "What game?" I'm Indian, so I'm only aware of one sport. We're good at cricket, and that's about it. So I don't know what Super Bowl is. So I need a volunteer. Who wants to be my test sample? All right, you're my test data point. So I'm going to try to predict for you whether or not you watch Super Bowl or not. So please do not answer that question. The features that I'm going to use are binary features, whether or not you're a domestic student or an international student, whether or not you've been at VT less than or greater than equal to 2 years. Okay? I measure that about you and I'm going to predict that. Okay, so let's see. Everybody else is my training data set. I'm going to assume, I'm making an assumption that you come from the same statistical distribution, right? The same population. If there's something unique about you, you should let me know. Alright. So y equals 0 means did not watch, y means watch Super Bowl, x1 equals 0 means just an order. It's not a preference. Domestic students are 0, international students are 1, x2, 0 means less than 2 years, 1 means greater than or equal to 2 years. Okay, so I first need to estimate probability of y, right? So let's do this. How many people are in class? 3, 6, alright, this is going to be hard. 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I'm going to ignore you two, you're not students. 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so 31 kids in class. Right? How many you don't... Yeah, I didn't count you. Yes, this is training data, right? So out of these 31 people, how many people did not watch Super Bowl? Wow. Okay. 2, 3, 4, 5, 6, 7, 8, 10, 11, 22 people did not watch Super Bowl. And I'm sure I messed up in my counting, so I'm not going to count the other one. I'm just going to assume that my counting is correct, and I'm just going to do 31 minus 22, right? So there's 9 here. Because I'm pretty sure if I ask people how many did you watch, I'm going to count it. So we counted that. The next thing that we have to do is we have to estimate the probability of x1 given y. Right? It's this 2 by 2 matrix. Y equals 0, y equals 1, x1 equals 0, x1 equals 1. So these are all the no's, right? So that's all the 22's. These are all the yeses, that's all the 9's. And I'm going to do some here as well. Okay. So out of the people who said they did not watch Super Bowl, how many of you are domestic students? I think we have found our feature. We have found our feature. So everybody who did not watch Super Bowl is actually an international student. Excellent. So out of the people who did watch Super Bowl, how many people are x1 equals 0 domestic? Out of the people who did watch Super Bowl, how many people are domestic students? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is going to be easy. Alright. 0, 1, 0, 1. Now we're talking about whether or not you've spent less than 2 years at VT or greater than or equal to 2 years at VT. So out of the people who did not watch Super Bowl, how many of you have been... No, let's do this. Out of the people who did not watch Super Bowl, how many of you have been here at VT greater than or equal to 2 years? You did not watch Super Bowl, and you have been at VT greater than or equal to 2 years. 1, 2, 3, 4, 5, 6. 6 out of 20. Excellent. Let's see, do some counting. 14, right? No. 16. Okay. The other ones are your 9s. Out of the people who did not watch Super Bowl.
Did watch.
Oh, sorry, you're right. Thank you. Out of the people who did watch Super Bowl, how many of you have been here less than 2 years? You watched Super Bowl and you've been at VT less than 2 years.
That's also for domestic students?
Yeah, we're not talking domestic or international, right? Remember, this is naive Bayes, so one feature at a time. You did what Super Bowl, and you have been, X2, yeah, you did what Super Bowl, and you have been at VT greater than equal to 2 years. Greater than equal to, yeah. We're talking about this case. You,
okay.
More than 2 years.
Yeah, greater than equal to, and you did what Super Bowl.
That's
None?
Sorry,
2.
Okay. 1, 2, 3, 4, 5, 6, 7. 7 out of 9. There's 2 of you who did what Super Bowl and who have been here less than 2 years.
Actually, there's 3. Oh, yes. Raise your hand.
There's 2 of you. The math is so much easier. Okay. Alright, so this is training, right? We're done with training. You've gone through your data set, you've made all the predictions. Test point comes in, and we need to know the test features. Domestic.
I'm international, I didn't watch this.
You're not supposed to say that.
I'm international, I've been here more than 2 years.
You're international, you've been here more than 2 years. Okay. Okay, so you're international, so you're here. And what we have to do is this. So there are only 2 choices, right? So here's what we need to predict. We need to compute probability of x1 equal 1 given y equals 0, and probability of x2 equal 1 given y equals 0, times probability of y equals 0. This is everything about the 0 clause. Right? How likely is the 0 clause? It's actually quite likely, given our prior. If we just go by our prior, let me see if I can calculate that. 22 by 31. So if we just start a priori by showing up to class, right? Here's what we believe about you. By showing up to class, there's a 70% chance that you did not watch Super Bowl because so many of your fellow classmates did not watch Super Bowl. Right? That's this factor. But we have to counter in the fact, what are these things telling us about your probabilities? We have to do that for both the classes. x2, x1 equals 1 divided y equals 1, x2 equals 1 divided y. 3 products. Okay. And then we do product 1. So posterior 1, I'm looking at y equals 0, 22 and 31, times, I have to look at x1 equals 1 given y equals 0. x1 equals 1, y equals 0. There was a 0 chance. Okay, we can stop the calculation.
That's x equals 0.
Oh, you're right. You're right. So 22 by 22. So 1 here, right? x1 equals 1 given y equals 0, and x2 equals 1 given y equals 0. 6 by 22. 6 by 22. Excellent. So, and I can't just do 1 minus. This is not a posterior probability yet because notice the normalization constant here is missing, right? So I need to go ahead and do the second multiplication as well. So y equals 1, that's this number, 9 out of 31, times x1 equals 1, given y equals 1, that's a 0, great. So I don't need to do any more calculations. And if I had done this, x2 equals 1, given y equals 1, 7 out of 9. Alright. So here's what I'm going to do. If I obviously proceed with this, we get a 0 probability of you ever watching Super Bowl, right?
Yeah.
And so we would be incorrect. But you can do a little. In practice, you would actually do a little smoothing here, right? You would say that I'm not going to allow 0 entries in this. I'm never going to place 0 beliefs. So you would add sort of pseudo counts here.
Yeah, it's actually not 0 because I am an international and I did work and I'm less than. Yeah, you missed the
Me
one.
too.
Me too, actually.
Wait, so you're international and you watch Super Bowl, so why don't you speak up? Okay. That only affects this column. Let me see if I can do this again. So people who
Just put the total 33 and add 2. I will make it instead of 2. Increase the number.
just put the total what?
31 to 32, 33. Number of people will become 33.
Oh, so I just never counted you? Like, you
Yeah.
just never.
Yeah, that's what.
9 and you just
Just
subtract.
minus it.
I never got chance to raise my hand.
You never got a chance to raise your hand. I see. So I would change all the numbers here. And just, like you're saying there's a 33 here and there's 9 plus something here. Okay, I'm not going to do that.
Just put 8 and 1.
Just put 8.
8 and 1 instead of 8. No, 4.
Wait, instead of
8 and
instead of 9? No, let me do this.
Remove one of the.
I'm just going to shift the distribution. Yeah. This is going to become 1.
No, 8.
And this is going to become 8. How about that? Okay. 8 over 9 never played up over there, so I need to do 1 over 9. Okay.
Instead of 91.
Still a small number, yes.
Just the 91.
You divide by
7 over 91.
7 over
9.
Thank you. Okay. And what I need to do is post 1, post 2. Right, this is our posterior probability, and P dot implies sum of. Right, that's the normalization. So the important thing is we started with some prior beliefs just by showing up to class. This is what we believed about you. There was a 70% chance that you did not watch Super Bowl. After we got to know something about you, the beliefs shifted in the direction of Okay. So after we got to know something about you, because of what we had estimated from this data set, the belief shifted that way. That there's actually even less chance that you watch Super Bowl. So do you want to explain yourself?
Actually, I think we choose a very bad testing point. Compared to,
I agree.
I think we don't come from the same distribution because maybe most of them are a graduate student and I'm an undergraduate student, so that's
That's a feature.
I'm a graduate, been here for a month. I'm a graduate, been here for a month, international, I watched the Super Bowl. So.
But okay.
But the majority of students are all graduate students. They mostly are international. And,
right. And what we'd have to do here is leave one out, right? I left him out, estimating parameters of everyone, and we'd have to go around, and that's how you get an estimate of how well this classifier is going to do for the next year or the next class. That makes sense? Okay. So that was the in-class demo of how you do naive Bayes, and this is essentially what you're doing in your homework as well. There's 2 classes, some number of features. But you're basically estimating tables like this. It's not difficult at all. This is a good example to illustrate the idea of anytime you're estimating. This column right here is the categorical distribution that we were talking about. When you went to your data, your categorical distribution came back with all heads, right? I've just never seen, or all tails. I've just never seen heads before, or so on. So you ended up with a distribution that is 1, 0. This is probability 1, this is 0. We've seen this in the case of a coin toss. What happens, we want to avoid committing to a parameter that is either 0 or 1. So what is the way to fix it? Priors, exactly, thank you. So what you put here on each of these columns and the class probabilities, you put different pseudo counts or priors. So the pseudo counts here, so that number that was going to add, 1 plus 1 everywhere, right? That number 1 is representing the coefficient of the beta distribution that is a prior on this column, right? This column is a vector of parameters for this categorical distribution, and I'm putting a prior value by adding that coefficient. Right? this adding of one or adding of these constants in terms of estimating these parameters is also sometimes called as smoothing or Laplace smoothing if you just add one. You just have to be born early enough and then you can name everything. just adding one is Laplace, it's special. But you'd have some sort of pseudo-counts here, some sort of pseudo-counts here, some sort of pseudo-counts for every single table. Does that make sense? Adding one is almost always a safe bet because it avoids, you're never going to see a zero in that case. Okay. Alright, so that's done. Here's a little subtlety of the naive Bayes classifier that is often useful to remember. We made an assumption that all the features are conditionally independent, right? That's why we just estimate these tables. But in practice, this is an assumption, right? The assumption may not be true in your data. It may be the case that if I go back to this example, that the people, so what did I try to measure? Grads, international. So here it seems clear that these two features feel independent, right? It shouldn't have to. Domestic students are also going to be at some point less than 2 years, at some point greater than 2 years. This is not going to be the case. But what if I started measuring other things like have you ever belonged to a fraternity, right? At that point you're pretty correlated with domestic versus international. And that correlation is not captured by Y. That has nothing to do with the Super Bowl. In addition to that. So that assumption, when violated, what's going to happen? So we just made the assumption that these two are equal. But if you, let's say in the worst case, you have one feature and you measure multiple copies of that. So you just measure the same feature 100 times. Your assumption is completely out the window, right? They're never going to be conditionally independent because as soon as you tell me x2, I know everything about x1 because they're identical. So what happens in that case? Well, let's say probability of x1 given y was a small number. Then you're just multiplying that same small number over and over again. And so you'll end up with estimates of y given x that are biased towards 0 or 1. Does that make sense? Because you're making an assumption that is not true, you're multiplying these numbers, you didn't have a chance to correct yourself. Like one noisy feature came along your way, you measured that 100 times and that will bias your feature towards, bias your posterior towards 0. That makes sense? So despite that assumption, naive Bayes is used a lot in practice. Often naive Bayes is used in cases where you did not realize it was naive Bayes. It goes under another name that we'll see in a little bit called bag of words model, which is just naive Bayes plus an additional assumption. We'll talk about that in a second. Okay, the other subtlety here that you need to be aware of that we actually saw in practice, what happens if you never see a training data point when xi is set to a value and y is equal to c. We saw that happen in our training cases. Another example of this exact situation is spam or non-spam, right? You're trying to classify emails as spam, and your features are whether or not you observe certain words, right? So if you've just never seen, every time Nigerian prince shows up, it's labeled as a spam email. You don't have friends in Nigeria, but then one of your friends just decides to go backpacking and sends you an email. Hey dude, I'm in Nigeria, right? At that point, you've never seen the estimated probability of, I've never observed Nigeria coming from a non-spam email. So at that point, it doesn't matter what else you see. This is coming from someone in my contact book. This is someone I know. This is someone I've exchanged emails with. All the other features can be 1, but this one particular 0 will kill the entire thing. And so you will just never predict the other thing. And that's why you need to add prior probabilities to this. Okay. And that's, we talked about this. This is exactly the Bernoulli data situation or the categorical divisional distribution. So everything is just directionally on every single particular column. You have a bunch of those numbers. You can either set them independently, or what's often done is set them to the same thing, right, at the same supercount. And then the map estimate is just supercounts. Okay. And in this case, your posterior probability will never be 0. You will never, for any particular instance x, ever have a 0-1 probability distribution, because you always have supercounts. Okay. here's a particular application of naive Bayes that is extremely common. It shows up in text classification a lot. You have a document or you have a web page, and you'd like to classify it as either a spam or a non-spam in case of an email, or what is the topic of the article, or you're trying to classify web pages. And the features are X. The features are the text, right? So here's a particular article, or just an email description. I can only comment on the Kings, but most obvious candidate, Alex Zidnik, highly touted as defenseman, clearly much more than that, great skater, hard shot. It's clear that this text, even if you don't understand, even if you don't do any linguistics, any natural language processing, it's clear that certain words are showing up. Defenseman, I don't know what that means. But a defenseman, you're talking about skaters, hard shot, some words are extremely highly correlated to certain categories. Right? So the features here are, you form a dictionary of particular words, right? And you represent your data as whether or not I see this word from my dictionary. And so probability of xi given y is how many times I've observed this word with this particular category. Right? So whether this is an email about a sports article, or it's a business article, or something. Does that make sense?
So you're counting how many times you saw that word, and then you're dividing by the number of words, or what are you dividing by?
I'll come to it in just 1 second. Give me a second about, let me define what X is. So here, if X, let's say your article always has 1,000 words. Let's say, I'm going to just look at the first 1,000 words in the article, whatever they are. And so you can define X1 through X1000. Those are 1,000 variables in your model. Those are 1,000 features that you're measuring. The state space of the features is a particular dictionary value, right? Is it word number 1, word number 2, word number 3, or word number 10,000? Right? English has some enumerable dictionary. And so now what you need to estimate is this particular thing, right? Naive Bayes assumption. The probability of observing the first word as skater, or the probability of observing the second word as skater for sports articles, for economics articles, for business articles, for other things. Right? Multiply all those probabilities together. It feels like here, this is not enough, this assumption is not enough, and it feels like somehow the first word or the 10th word shouldn't really be treated separately. Right? Yes, we did measure 1,000 features, but our features are essentially the same thing measured over and over again. Right? So this is often called a bag of words model, where you make an additional assumption that you make an additional assumption that it doesn't matter what your feature is. The probability of xi equals little xi is the same as xk equals, actually that's correct. I should just change that to xi equals a. So this assumption is called, this is an extra assumption where you basically say that no matter what feature I'm talking about, that I only need to estimate one table. I don't need to estimate one table per feature. Right? If you think about the example here, this was feature number 1, this was feature number 2, there was a table here, there was a table here, and we expect these tables to be different because these features are measuring something very different. In text, a lot of times, the features are essentially identical. It doesn't really matter whether we're talking about the first feature or the second feature, and so you'd like to estimate a single table. And that's what that assumption is. It's called a bag of words model because it assumes that a sentence is literally an orderless bag of words. Right? It doesn't matter whether a word appears in the first position or the second position. So you can have a sentence that says, when the lecture is over, remember to wake up the person sitting next to you in the lecture room. Right? That's a sentence. X is what are the words present in this sentence, and we're talking about probability of y given x, right? And this y given x would be identical if the sentence was this, or if the sentence was, in is lecture, next, over, person, remember, room, sitting, to wake up when you. Doesn't really matter what the order is, because all we're measuring is the occurrence of a particular word, not the location or the linguistic structure. Right? Hence, bag of words. That make sense? Why is bag of words useful? Because you just assume that instead of estimating 2 or 10,000 different matrices, you just have to estimate a single matrix. On the x-axis of the matrix, the feature is the dictionary count, right? How large is the English vocabulary? On the y-axis, or how many categories? This is sports article, finance article, and so we're just talking about what sort of words do sports articles talk about, use, what sort of words do finance articles use, and what sort of words do. Doesn't really matter what position you're going. That makes sense? And if you think about it, this is exactly what this class started. In the intro class, we told you that you can represent a text document as a frequency counts, and that's what backwards model is. That it doesn't really matter where these words show up in the text, the only thing that matters is their frequency counts. Because that's what's going to happen here as well. Does that make sense? Okay. This is also often done in computer vision, where you take an image, and if you're trying to predict what object it is, you try to represent it as a bag of parts or a collection of words, except these are not words as in coming from the English vocabulary. You have to define your own words or parts of the object. So you have to represent a face, for example, as a collection of an eye, a nose, a chin, and a mouth, and parts of the head. And again, what you're assuming is it doesn't really matter where these words are located in the sentence or what their order is. All that matters is I saw an eye, I saw a nose, I saw a chin, and if you observe enough of those, that has to be a face. If enough words are used, then it's an article about a certain kind. Does that make sense? Okay.
And did you know if it's an eye, for example, or a nose or something? Did you do like K, something?
You have to train a detector or a classifier for an eye. So you have to have an eye detector, a nose detector. So you've broken down a large problem into a collection of small. And you'd have to do this not just like there are finance articles and there are different kinds of articles, there are different objects, and you have to have a vocabulary of words that contain parts from the vocabulary. So just like you have to define an English vocabulary, here you have to define vocabulary which are some parts from all of these objects. And what you're going to do at test time is represent, just like it was frequency of counts of words in text, this is frequency of counts of words for different parts. So how many times did I see an eye? If you see 10 eyes, it's got to be a face, right? Because it's just looking at, if I see an eye, then it contributes some towards the score of seeing a face, and so on. And there are no eyes that happen in a bicycle, but there are these other parts that contribute to whatever I'm using this for.
So it would be very hard to distinguish between a bike and a motor.
Exactly. It will be difficult because the parts that you end up learning will be wheel-like parts and will then happen in motorcycle. Just like if you define fine-grained categories of text articles, right? If it's macroeconomics versus microeconomic articles, they'll use the same words. Then you have to do some fine-grained reasoning. You just can't look at what words are present. All right. Let's see. And the way this is often learned is that just like you have to have an English dictionary of words from images, you also have to learn a dictionary of visual words or what words represent this language of objects. And that's usually done with algorithms like k-means and clustering. We haven't talked about these algorithms. We'll talk about them at the second half of this, after the entire class. And then, at test time, you learn basically your classifiers given a histogram over these words. So you represent each object as a histogram over these words, and those are your counts. And you use like basically. All right. What if we have continuous variables? So everything that we talked about so far, the features here were discrete, right? They were discrete, so we assumed that this was a categorical distribution, and MLE resorted to counts. You can have continuous X, in which case it's, for each pixel, what is the intensity? If it's not a binary image, what if it's a real value from 0 to 255 or some continuous value, right? So then the assumption that you'd have to make is X given Y is not categorical, X given Y is Gaussian. Right? Some family of distributions, for example, for class, I don't know, let's say we're talking about this pixel, right? Or some pixel here, Xi is some pixel. For class B, that pixel value has some mean and some variance. Right? Usually when people write some digit or some characters, there's a pixel in the center that's usually turned on, and so it has some mean and some variance value. Right? So there's a mean parameter I, because we're talking about the ith pixel and the ith variable, k, because we're talking about the kth class. And so there's a ith feature, kth class, mean parameter, ith feature, kth class, variance parameter. Right? Those are the only two parameters that you have to learn that define a Gaussian distribution. Compare that to k or whatever the output space of, whatever the space of x is. And that many parameters you have to learn for every x given y. Does that make sense? So you would put a Gaussian distribution. And you can often make assumptions like, you can often assume that the variance is independent of y or the variance is independent of xi. These assumptions that will help you reduce the number of parameters, because the number of parameters here is for every feature and every class, I have 2 parameters. Right? You can help reduce that by saying that the variance in feature values don't really depend on what class we're talking about. That usually it's the same variance. Or you can say that the variance is independent of what feature we're talking about. There are certain variances for certain classes. That makes sense. But this is the most general model. And we've already done this. We've looked at maximum likelihood estimates for these parameters. Right? We know how to fit parameters if a Gaussian given data points. In this case, if it's mu ik, it would just resort to go find pixel number I for all data points that are labeled k and just take the average of them. Right? That's the mu I. So forget ik, right? We know how to estimate the mean parameter. Go to your data, take the average. That's the MLE. Go to your data, just compute the sample variance. That's the MLE you estimate. Ik is just, it's just restricting what data points you can check. Does that make sense? Okay. So at this point, we are done with naive Bayes. We expect you to know certain things about naive Bayes. We expect you to understand the connections to making optimal decisions using the Bayes classifier. We need you to understand what assumptions we're using, what are ideal cases for this assumption, when can this assumption help working it out. For example, if I give you a data set where the assumption seems to be satisfied, let's say it's a question in the exam and I show you visually a data set, you'll have to be able to check that, does it look like the features are independent given class in this particular data set that I've shown you? Visually speaking, not analytically computing it. Okay? And why is Bayesian estimation of naive Bayes parameters important? What sort of problems can lead you there? What a bag of words model is, and what Gaussian naive Bayes is. And similarly, you can do Laplacian naive Bayes or any family. What we are calling naive Bayes, what we call naive Bayes in this lecture is categorical naive Bayes. Right? You put a categorical distribution, then you estimate the parameters of that. You can put any other distribution and estimate parameters of naive Bayes. The key assumption is conditional independence. Makes sense? Okay. So let's start on the next topic, which is logistic regression. But we'll need next lecture to really get through it. So let's start on this. So stepping back a little bit to where we were, we started this class saying if we only had access to posterior probabilities, that would be awesome. That would lead us to perfect classifiers. The generative approach said, okay, let's use Bayes rule and fit this. We cannot fit this, let's make certain assumptions. This we can fit to data directly, let's use these two. The discriminative approach will say, let's go for probability of y given x directly. Why are we estimating this if all we care about is this? Okay? And that's going to be something called logistic regression. So what we'll do is we'll think about a two-class problem. So y can only be 0 or 1. And we'll think about directly regressing to that probability. It's going to be extremely silly, but we'll see if we can do it. Okay. So it will also tell us why this is called logistic regression. Okay, so the input is x, and let's say that lives in some RD, so that's continuous. The output is y, and let's assume for simplicity that it's binary, and 0, 1 because it'll make life easier for me in a little bit. Okay, and so what we're interested in obviously is probability of y given 1 given x equals ln x. So this is just some number. If we can estimate this number for every x, we're done. And this is a number, we know this is a Bernoulli distribution. It has to be some number theta, it has to be some function of x. Right? So how about we try to regress directly? And here's one idea number 1. This is a silly idea, but why can't we do this? Why can't I say theta hat is equal to W transpose x? Then what I'm going to do is I'm going to measure my features and then just multiply that by a weight vector and call that my probability of class 1. Why can't I use that? I have data points, and what I'll try to do is every time I see a data point xi, yi, every time that's labeled 1, I'm going to feed that into my regressor with the regression value being 1. And every time I see y equal to 0, I'll feed that into my regressor with, let's say this is x, and this is y, 0, 1. Maybe I'm measuring a single value thing. Right, there's some x. I'll feed this with a regression. I'll feed this into like a linear regressor or something. That'll give me a parameter theta. Why is this silly? It's silly. I can see it on your faces, but why is this silly? What problems could you land into? Theta has to be less than 1. Excellent. Theta has to be positive, theta has to be less than 1. There's a range of theta that you have to do. This thing is great for predicting real value things, right? This is going to predict a real valued quantity, and what we need is something that goes between 0 and 1. Right? Can we crunch the real number line into a range of 0 to 1? It's like a hack on
put some bounds on
Sigmoid
yes,
function.
Put some bounds, sigmoid. Thank you. So meet the sigmoid function. This is called, often indicated as 1 over 1 plus e to the negative c of c is the thing. Right? It's crosses. This is z. This is sigmoid of z. Has an asymptote at 1 and 0. If z goes to infinity, z starts going to infinity, this term vanishes, e to the negative infinity, so you get 1 over 1. If z goes to negative infinity, I just have to multiply by e to the z on both sides, and the ratio goes to 0. If z is equal to 0, I get 1 over 1 plus 1. So it crosses the line at half. Does that make sense? So this is a function that essentially crunches down the entire number line into a range of 0 to 1. Excellent. Never actually predicting 0 or 1. Perfect. Even better. No certainty, right? So here's idea number 2, which is let's make, so instead of y given x, making that Bernoulli with parameter W transpose x, we'll make it Bernoulli with parameter sigmoid of W transpose x. Just regress to a number that's a score. Don't treat it as a probability, treat it like a score. Crunch it down from the real number space to the 0 to 1 space, and that's your parameter. And that right here is what is known as logistic regression. Logistic, because this function is often known as sigmoid or logistic. Regression, because you can sort of see the connections to regression. You can see that you were initially naively trying to regress to a number, now you're trying to regress to a number past the signal. Does that make sense? And in your head, you can actually compare this to regular or ordinary least squares regression, where we said that ordinary least squares was Gaussian. And if you remember, we had made the connection from ordinary least squares to this sort of a model where y given x was a Gaussian centered at W transpose x. So make that connection between that and this right here. Right? So Bernoulli of a sigmoid versus a normal centered at W transpose x. And you can see the connections to regression. Does that make sense? Okay. The idea is fairly intuitive, that we're going to regress to this, that there's a number theta, and that tells us this probability of y. And so what this does is, this gives us a really simple expression for logistic regression posterior probability. It's just 1 over 1 plus e to the negative W transpose. Right? This is a logistic regression model right here, that you're assuming directly a form for the posterior probability instead of estimating the feature given x, multiplying that by y, feature given y, multiplying that by y, and trying to compute the posterior from Bayes rule. Just directly assume a form for this and directly estimate w from data. Does that make sense? It is more straightforward in going for trying to model directly what you care about. Okay. The interesting thing about this, even though I came from it from a probabilistic classifier, Bayes connection, here's the thing to keep in mind. So we said probability of y equals 1 given x equals little x is 1 over 1 plus e to the negative w transpose x. What is probability of y equals 0 given x equals little x? So we do the math lazy. What?
1 minus.
Yeah, sure. That simplify that quickly.
E power of minus w.
Thank you. E to the negative w transpose x divided by 1 plus e to the negative w transpose x, which is also equal to 1 over 1 plus e to the negative w plus w transpose x. Right? It's really nice how the forms are nicely symmetric, so you can interpret this as a score for class 1. The larger the score, the larger this number, and the smaller the score, the larger this number. Does that make sense? Okay. The other reason why this is going to be interesting is just a couple of minutes and then stop. This is probability of class 0, this is probability of class 1. How do I know which one to predict? Whichever one is
Greater.
greater, thank you. So I just need to, one way of doing that is I can check the probability of y equals 1 given x. I can take the ratio of probability of y equals 0 given x. And if this ratio is greater than 1, then I know what to do. Right? I just need to check this. Is the probability of 1 larger or the probability of 0 larger? And I can also take the log of both sides. Why? Because math is easier. Right? And it becomes clear what this is going to lead to. So that denominators get cancelled. Right? I'm going to use this form and this form right here. The denominators get cancelled. I get log of 1 over e to the negative w transpose x. And I have to check whether that's greater than 0. Excellent. So log, I can take the inverse, and this is the same thing as checking whether w transpose x is greater than equal to 2. Right? So you're going to make a prediction of +1 if this score is greater than 0. You're going to make a prediction of -1 if this score is negative. So logistic regression, even though it looks, however we arrived at this, it's essentially a linear classifier. Right? You train some weights. There's a W0 plus W1 x1 all the way till WD xd. And notice there is also usually a bias feature here because you can stick a bias. There's a bias feature here and so a bias weight here. And you're just checking whether that's greater than or equal to 0. And this is the equation of a hyperplane. In some d-dimensional space, you're learning a hyperplane. On one side of the hyperplane is class 1, on the other side of the hyperplane is class 0. Does that make sense? And there's a nice sort of, there's not just a score, you know what is the probability on this side. The higher the score, the higher the probability of class 1. Does that make sense? Okay, let's stop here and we'll pick up next.